The first law of thermodynamics has a pretty simple definition. In fact, it is just that the internal energy of the universe is constant. And the internal energy can be defined as U, which is the sum of the potential and kinetic energy of either the system, the surroundings, or in this case, what we're talking about is the universe. However, there are a lot of details that we need to talk about in this video, from defining heat and work, and then overviewing 3 different equations that can model this single idea. So let's start by defining heat and work, and what I'm going to use is this little Venn diagram here. And the one thing that heat and work 100% unite on is the fact that they both are terms that define energy flow. So we'll use the same unit. We will usually use joules. You might see kilojoules or calories, even kilocalories, but they are both functions of energy. So let's start by talking about heat. Now, heat is going to be disorganized motion. And if we want to add a second layer to this, it's definitely going to be molecule oriented. And what in the world does that mean? Well, if I drew a box and put a bunch of, let's say, gas particles inside this box, if I wanted to talk about the heat of this system, I would be referring to the fact that these gas molecules are all moving around in random directions. So there's no organization to this. They're just a bunch of gas molecules and they're doing whatever they want. Each molecule sort of has a mind of its own in this respect. Now, if we switch over to work, this is going to be organized motion. And so this is going to be system oriented. And so how does this differentiate from that box of gases? Well, now I'm going to draw something where there's actually a task to be done. And so I'm going to be doing a shriveled up balloon becoming just a glorious and filled balloon. Now, in order to make this happen, the gas molecules that are in this balloon needed to all expand outward. And in this case, what's happening is the system is actually working together to expand the volume of that balloon. So this is a system-oriented, organized task. And so the way I differentiate heat from work is there an organized task that's being done? Are you increasing the volume where the system is all working together? Or are you looking at just a box where those gas molecules are all going in different directions? Moreover, heat is typically associated with going from high to low temperatures. And in fact, there's often a temperature change, not always, but that is usually a good indication of heat flow. Next, we're going to talk about the vocabulary associated with the signs of heat and work. So when it comes to heat, you can either have an endothermic or exothermic change. And so I'm going to use this diagram up above to kind of explain this. So if you think about where the chemistry is happening, this is always going to be your reaction system. But as a chemist, and if you're trying to be a safe, responsible chemist, you are usually standing out here in the surroundings doing your experiment, and hopefully you've got your safety goggles on and your lab coat and everything. Great little stick figure there. So here's why this is important. When we're talking about an endothermic change, we're talking about heat going into the system, and we're talking about a positive heat flow. But why is it that endothermic reactions, if it's a positive heat flow, feels cold? Well, the reason is because you are standing in the surroundings of that chemical experiment. So you're actually feeling the heat leave the surroundings to go into the system. It's the same thing with an exothermic reaction where heat is going out of the system. And what's a common exothermic reaction? Well, an explosion, a combustion reaction. In this case, the heat flow is negative, and you're feeling it getting hot because you are standing outside of the reaction system. So you're actually feeling all of that heat escape the reaction system, and you're in the perspective of the surroundings. Now, for work, you have work done on the system. And what that means is you actually have an external energy applying the force to your system, in which case your work value is positive. Or you have work done by the system, which means your system is operating that organized molecular motion, which is actually costing your system energy. So now let's go back to the first law of thermodynamics. And the first equation that I want to talk about is this one right here, which is that the delta U for the system, so the internal energy change for the system, is equal to the heat flow and the work. And this is an equation that you're going to use a lot. And it's important to recognize the subscript here. We're talking about the delta U of the system. And so number 2 is going to bring in the delta U of the system is equal to the negative delta U of the surroundings. And what that means is any amount of energy that is going into the system is coming from the surroundings. So that's the loss from the perspective of the surroundings. And you can add on to this to say also that Q of the system is equal to negative Q of the surroundings, or that W of the system, or work, is negative W of surroundings. Now, the third equation that brings this all together and finally gets us to the definition of the first law of thermodynamics is that if the delta U of the system is equal to the negative delta U of the surroundings, and if all of this, the system plus the surroundings, is the universe. So what does this mean? Well, it means that if they are opposite in sign but equal in value, then delta U of the universe is constant or just equal to 0. So this kind of explains the fundamental concepts behind the first law, but now let's see if we can apply it to an actual question. So here we have a pretty straightforward question dealing with the first law. And what it says is that a chemical reaction releases 15.8 kilojoules of heat while 2.4 kilojoules of work is done by the system. And part A is going to ask, is this reaction endothermic or exothermic? Part B is going to ask, what is the value of delta U for the system, surroundings, and universe? So really we're going to use all those concepts, understanding how our vocabulary can affect the sign of heat and work. And then we're going to use those 3 equations that we talked about for the first law of thermodynamics. So first, to answer, is this reaction endothermic or exothermic, we need to remember that endothermic means you are absorbing heat and exothermic means you are releasing heat. So if we're looking at this question, a chemical reaction releases 15.8 kilojoules. That means by definition that this is exothermic. But there's another important thing that is implied by that vocabulary. And that is that the value of heat here, that 15.8, if I need to plug it into an equation, has to be negative. So if I'm looking at this and I want to answer question B, which is what is the delta U for the system, let's focus on that for now. That means Q is going to be negative 15.8 kilojoules. And then we can do that same idea for work. Remember, work done on the system is positive, work done by the system is negative. So we're going to add the work term, but we need to know that work is done by the system. So the work value is going to be negative 2.4 kilojoules. And this is important because it will absolutely change the value that you get. Because if I had either one of these positive, I would end up with a totally different answer than the correct answer here, which is negative 18.2 kilojoules. So I can write here that delta U for my system is equal to negative 18.2 kilojoules. Now, for delta U of the surroundings, we need to remember that delta U of the system is equal to negative delta U of the surroundings. So there's not a lot more math that we have to do here, except to say that our delta U of system was negative 18.2 kilojoules. And so our delta U of surroundings has to be positive 18.2 kilojoules. So delta U of our surroundings is positive 18.2 kilojoules. Now, our delta U of the universe, we can look at it from two different ways. We can actually calculate it now that we have delta U of the system and delta U of the surroundings. It is just going to be the sum of those numbers. But we also know that it is just always going to be equal to 0. And so these are our three answers here. And so this video was just a gentle introduction to thermodynamics, but I want you to be able to think about how we can use vocabulary to tell you whether a reaction is endothermic or exothermic, and how we can use these equations to actually calculate delta U of the system, delta U of the surroundings, and delta U of the universe.